Let's see. All right, good. All right. What we'll do today, I do want to talk a little bit about mathematical economics, and so let's do that. But I was thinking, because I thought maybe someone would ask me about the election, I thought I'd use that as sort of a segue into what we're going to talk about. It's not so much commentary on the election as it is commentary on mathematics and statistics and whether or not those things are useful at all. And I think probably I just want to draw some analogies, which will actually kind of, at least do it a little bit, cover to what we're going to talk about partly today. Mostly I want to talk about some more discussion of economics of climate modeling, and so we're going to do that. And I think I probably will not really present the Lemoine and Rudick paper today, but we will get all set up to cover it. How many of you have read the paper and understood it, do you think? Who's read it? The second one. So the first one is Economics of the Climate by Heel. Okay, so you should definitely have read that one. And basically it surveys a number of things, and some of it might be sort of he assumes you know a lot of stuff that you might not know. And I'm going to be talking about those things to try to make this increasingly clear. I have to say that what we're going to be doing on some of this stuff is going to be kind of arm wavy, but I'm going to give you at least a picture of what goes on with this. So we were talking about discounting and dynamic problems, and we're going to get back to that. But then the other paper is here it is. The Lemoine and Rudick. This is the steering the climate system. This is the one that I really want to get to. Okay, so we will get to that. So one of you has read it so far? Two or a couple of you. Could you guys make sense out of it much, or kind of?
The first part was pretty clear, and as it went on, I started to get a little bit.
Okay, and then it also has an appendix that I did not include, which is like, this will seem like kindergarten stuff compared to the appendix, so we won't read the appendix. That's often the way it is with these papers, is that there's an enormous amount of proofs and things that are in the background. Is any of this stuff useful? And of course, some of our courses here, like I teach Austrian too, and Mises says there's way too much math, and probably, and I think if you properly understand what he's saying, what he says makes sense. Some people just have, some economists, Austrians especially, just have an allergy to math almost, and they just say, oh, we should dispense with it, or it's not useful. Murray Rothbard really attacked the use of mathematics. But can this stuff be useful? Do you guys know what yield switching is? Probably not. Yield switching in farming, in crop insurance. None of you have heard of it. This is an interesting thing, and I wouldn't have expected you to know about it. But yield switching is an idea. Let's say that a farmer has two fields. So we're looking down at them, okay, and there's wheat, corn, something like that growing in them. Same crop. And he's got two separate fields. And he's gotten crop insurance on both of them, okay? Yield switching is an interesting technique in which you have crop insurance. And so the way that crop insurance works, of course, is if your harvest doesn't come up, or if your crop doesn't come up, you get covered. But also, if you have a big shortfall, a sufficiently big shortfall in your harvest, below average, way below average, depending on how much it falls, you get an indemnity payment. Okay, great. There's various kinds of crop insurance the way it works, but this pays for a low harvest. Okay, great. So we've insured both fields, and we get an average harvest on both. Okay, we got an average harvest on both. And so in year one, what we do is we take the crop that we harvested from here and pretend that we had a bumper crop here. We got almost nothing here, but we got twice as much as usual here. Okay, that's year one. This is the simplest form of yield switching. And then we got nothing here, so we also get an indemnity payment. Cool. Now that's actually illegal, that's fraud, but it definitely happens. because we pretend that we got the low harvest here. We didn't, it's all wheat. It all looks about the same. We all test the same. We've same variety and everything, and so there we get the crop plus we get the extra payment. What do we do next year? Well, if you keep doing next year, what you do is you switch, and in year 2, we take the harvest from this one and claim it all came from here and get an indemnity payment on that one. Okay. Great, yield switching, and so now we can harvest, we can farm the insurance, as they call it. Great. Now I won't go into all the details of how this works because that also affects your average harvest here, which means that in the future you won't be able to get as high your insurance premium goes up, and you don't get as much coverage in the future because your average harvest is dropping. And when you do this, if you're not careful about it, you can get yourself out of the insurance market. Okay, that's the simplest. The way this really can work well, suppose you've got, like, let's say 1, 2, let's just put up a whole bunch of fields. Okay, I don't know. And let's see, I own those, my brother owns those, my son owns that one, my cousin owns that one. Okay, there are a bunch of family farms, and this is not an uncommon situation. Oh, and we just pay each other off in this. We just all work together, and we switch it from there to next time it's going to be there or whatever. We just think of some weird pattern that'll be really hard to detect, right? It's not like the 1, 2, 1, 2 back and forth, which that's a pattern you'd notice. Great, that would be harder to find. The firm that I worked for developed software that a program that could be used to detect patterns like this, the complicated ones. I mean, if you saw this, so in year 1 you saw this, and in year 2, 1, 3, 5, year 2, 4, 6, you'd probably start getting suspicious, right? You'd probably get suspicious, but you would not have anything that would stand up in court, but you would know where to look. We see that over with these 2 fields. Let's go investigate there and look more closely. Well, our software the firm software that we developed and just gave to the federal government for detecting this, the yield switching software would detect this kind of behavior in a more complex pattern. And it would tell the risk management agency where to look to see, okay, there's an area where it doesn't prove that there was yield switching going on, but that's a suspicious area, go look at those guys. Okay, that's where you should put your investigative effort. And there is a lot of that goes on. And so, great, well there's the thing. So that's useful. What does that got to do with the election? Oh, well, it does actually maybe have something. Here's what some people have argued, and I can't vouch for the patterns, but you've probably seen these, and that's that here's the total number of votes in a state, let's say. Total votes, and on that axis, what do I want to put? I don't know, time, because we're counting over time. Okay, great, that's time. That's where we're counting the votes. And what seems maybe to have happened, well, what you would expect is, I don't know, something like, okay, there's candidate A. The totals should be increasing as time goes on. And the way I've drawn it is, I have no reason to think that it should do that, except that apparently that is what is observed. But as you go through time, the amount of votes declines, because first of all, I don't know what's going on. I guess a whole bunch of places report, and then a few others, and finally some outlying districts or something. And then candidate B is going something like that, A, B, and that's in that story pretty much, I guess, hands down. And another pattern that I just started thinking about how these things might work. You've got candidate A, and maybe candidate B is going down, and then you start counting some area, and I don't know, the big cities start flowing in, or something like that, or something. Or you see something like, you might see another pattern, and then, oh, it turns out B came from, so it came from behind, so to speak. Or you might see this, candidate A, and then candidate B, something like, you might see some patterns like that, okay? Okay, we'll figure it out as the vote goes through the night. What would you think if you saw this? There's candidate A, and there's candidate B, like that, okay? What would that make you think? Now, there are, so did that happen? At least it's claimed that happened in Michigan and Wisconsin, that you see these kind of discontinuous breaks, and that's what has aroused some, okay, what does that show? What's the probability that all of a sudden, what's the explanation for that? That all of a sudden there was 100,000 extra votes for B, like a big chunk of votes. It just suddenly all came in, all for B, and 0 of them for A at that point. Okay, that sounds like a low probability event. I could flip a coin 1,000 times, and I might get heads, but if I did that, I might start thinking, was there something weird about the coin or the coin flips? It is possible to just take a regular fair coin and flip it 1,000 times and get all heads, but I might get, that would be a thing that would make you suspicious if you got that number. You can't rule out that that's what happened. Just as here, some people look at this, and those people happen to be Trump supporters, and they look at this and go, wait a minute, what happened? That's Biden and that's Trump in Michigan and in Wisconsin. So that's why, that's part of the discussion and debate. And so maybe there's something that that's interesting to investigate and wonder what's going on. And it's just like with yield switching. Haven't proved anything, but there is some sort of, you can see what the arguments are about.
Just some follow-up on that too. What happened in both situations was there was a county that had like almost nobody in it, and their person who was entering the data accidentally entered it in order to more. So like here's in the UP, there was one county where for votes for Biden, they actually put a 0 after it. So instead of 15,000, it was 150,000. And it was reported and fixed like within an hour of it happening.
Mm-hmm. There's been various kind of odd things, other things. What's that?
Milwaukee received 183 absentee ballots turned in, which is 83% of the voting population in Milwaukee. So that's like not even just registered voters, that's just the voting population.
I'm actually not even done with this stuff because I'm going to move it to, well, I'm going to put this on climate in a second, but or something. I don't know what I'm going to do. There's a lot. There are many. I always think of my relative. You know what steel is in Russian? Stalin. Yeah. So I always think of my uncle who used to run the Soviet Union. I believe there's no relationship at all, and that was not his real name. That was one he adopted. That was his revolutionary name to show that he was as strong as steel or something. But he did apparently once say that it doesn't matter who votes. What matters is who counts the votes. And I always think that's very wise. That's wisdom, I guess. But at any rate, there are many other things that people say, well, it's an anomaly. It isn't proof of anything. It explains why there's suspicion, and those sorts of things. I'm going to say anything more about that. Anyway, well, okay, so maybe anyway, that's, I guess, interesting. Let me change what we have on the axes here and show something that looks very similar to this. It's not the same thing, but the principle is a little bit, I don't know, the graph, just one graph reminded me of another. Okay, time and carbon emission. And this is actually my representation, just because it follows from what I just talked about, of in the Lemoyne and Rudick paper on page 2955, panel C. And they draw it a little differently because they're trying to be more accurate than I am, more true to what they've calculated. But suppose that we were thinking we had to employ, we were going to put in a carbon tax so that we reduce the emission of CO2 and do it optimally so it will not create, unacceptable global warming. But at the same time, we want to do it optimally so we're not inflicting unnecessary costs on the economy. And so we calculate the hoteling path, and we get something like, I don't know, there's the hoteling path for carbon emissions. Okay, great. We just found the optimal carbon emissions, and Lemoyne and Rudick say that we have failed to take something into account, which is basically carbon decay and carbon, really two things. The forcing, the fact that there is a lag in carbon emission to the time that it has its temperature effect, and also the fact that it decays has not been properly taken into account. And they say, given that, the optimal path is not the hoteling path, but it might be something like that. This, I guess we'll call that the Lemoyne and Rudick path, which is L and R. And their claim is that that is optimal, and that that's better in certain respects because, first of all, why is it better? First of all, you get the gain. They're taking into account the gain, the fact that the carbon decays or disappears, and also that it takes a while for the full effect of the carbon to have on the atmosphere or on the temperature. Taking that into account means that we can put more out right now, and so the gain is additional current output or income. Okay? We get that up front, and then we can invest it or do whatever, and so we get that current income or near future. And then later on, we will cut back more drastically. After we're rich, so to speak. We'll be richer and better able to afford it in some sense. Okay, great. And maybe even, they don't say this, but maybe even have better technology for doing it and better understanding of how to do it and better models, et cetera. So we get earlier economic growth and decay by doing it this way and as opposed to this way. That's what their argument is going to be. So you can get what they're getting at. And then they'll work through the mathematics to show how this works. So we already know what the result is, so to speak. Okay, cool. All right, any questions so far? Okay, last time I don't know whether anything I said was clear or not. Did it make sense last time? I mean, I have Lauren and Elaine sit there. No matter what I say, they go, "Yeah, this is great." They're just they're from the sports teams, and they're just supposed to be positive. So I never believe anything they say. Oops, they're probably watching on video. Actually, I believe every word they say. So let's clear this. Oh, what I said last time, I set up the idea of the Ramsey model. And again, that's one where we're just maximizing utility for the average consumer or the average agent, the average person in the economy. We assume they're all this, we use a representative agent, so everybody's the same, so it applies to everyone. And we maximize the discounted sum of their utility stream forever. And subject to a constraint that you can't consume more than you produce. And the difference between consumption and production will be your capital stock, the change in the capital stock that you have for next time. But you also have to take into account depreciation and growth of the labor force and things like that. And that gives us a set of first order conditions, and it all seems pretty straightforward, right? Should I write it down, or is that clear? Yes, I really like it. Should I do this or this? And the answer is yes. Okay, good. Thank you, comrades. Everyone is agreeable. What would you like me to do? Well, what you'd like me to do, forget that part. What should I do next? Yes, okay, good. All right. Let me go ahead and, we were talking about discounting last time. And I wanted to pick up and, where did I leave off? Not right there. I guess I was doing social cost of carbon, and I think that was clear. Let me just give you a little bit about the Ramsey rule for discounting. And again, it comes out of this model. We'll go ahead and I'll just say that it is, what we're going to do is maximize utility, and we're just using whatever notation, and that's going to be the sum from 0 to forever of the discounted, so it's e to the minus rho t, what is it, u of ct, and c is going to be subject to the law of motion, is just going to be equal to our capital stock minus depreciation. We should probably write this down carefully. Minus the capital that we lose, which was, I don't know, the way I had it written here, we're gonna be switching notation anyway, is the, okay, that's the amount of capital that gets lost to depreciation, and then we also had to increase it, because here we were taking into account population growth. And this is per capita capital, and then we've got plus the, so put a minus and not use extra things, plus the part that we set aside for accumulation of capital next period.
Sorry, is that K1?
KT, it's a T, yeah. KT, right. So it's whatever we produce in this period. Okay, our consumption is the, again, that simply is rewrite that this way. There's what we produce, this is maybe easier to interpret. There's what we produce in this period, given our capital stock right now, okay? But then we have to realize that some of it depreciates or is used up. Okay, and I also put the N in just to show there's population growth, because we're doing it on a per capita basis. And if there's no growth, that's just a 0, so don't worry about it. And then minus the part that we consume. That is to say, our income minus consumption minus depreciation, depreciated capital, equals the change in capital. Okay, great. That is to say, you had $100, you consumed $50, $2 of capital are depreciated, and so you got, it's $48 of new capital that you've added to the stock, or whatever it is. Okay, cool. All right, and out of that, we then, set up a bunch of first order. You take the derivatives and set up first order conditions and things like that, and that's just what I want to jump to without doing all that, those steps. And what I want to show is the Ramsey rule, because they employ that in the Lemoyne and Rudick employ this in their paper. Okay? And so the Ramsey rule for discounting in one of these models. And this will explain what it is that these guys are up to when they start writing things down. And this is discussed on page, in the Heal paper. Is it Heal? It's Heal, not Healy, but I think I wrote it down there. So the Heal paper, page 1047, if you want to go back and look at that. The Ramsey rule is that your interest rate that you will use for discounting, this is also called the, well, it's called the social discount rate. The social discount rate is equal to, and we'll use, I think this is the one that they use in, I'm just going to use my own. I think this matches basically what Rolomoy and Rudick do, so rather than what Heal does. But rho is going to be that's your pure time preference. That's your discount rate for time preference, okay? Subjective time preference, now to later. That would go on utility, so pure rate of time preference. And this one will be the elasticity of marginal utility of consumption. And this one is the growth rate of consumption. Okay, great. So this thing is called the social discount rate. It's also called the CDR, which stands for consumption discount rate. And this one is, of course, this one will be in terms of dollars, and that one's in terms of utility. We're finding a way to convert subjective utility discount rate and discount rate in terms of dollars of consumption, and this comes from the Ramsey model. And here's the logic of the whole point of what's going on here. Suppose we consider consumption at two different points in time. So the 2 points in time, we're going to consider a unit of consumption at well, I guess I'm saying it that way. It's at time 0 and at time t. And at t, t is greater than 0. Okay? And this is just being done continuous. What do I want to say about this? That will also give us utility for each one of those things. And therefore, here's the question. Suppose I could have one extra unit of consumption at time t. I can have one extra unit of consumption at time t. What would I be willing to give up today to have that? What would make me indifferent? Where I'd be willing to do it, and we're just going to say a certain amount xt. And that's not indifference. I have a tendency to do that, but I'm using that symbol for too much stuff, so let's not do that. What I'm willing to give up in consumption today for one more unit of consumption at time t, okay? And so what's my gain in that case? The gain that I get, it would be u prime of ct, okay? that's what my gain in marginal utility will be at time t. And what am I giving up? My loss. I'll call it a cost. And the cost would be xt times the marginal utility of consumption at that point. The marginal utility times the amount of stuff I give up, okay? And it's being evaluated at a point. So it makes sense, right? That's what the cost now and gain at time t. Cool. All right. And so I know that with indifference, it must be the case that xt u prime c naught is equal to e to the minus rho t, my discount factor, times u of c naught, okay? Great. That discount factor there is, of course, that's the subjective rate of discounting. Good? Yeah. No, it's not terrible. What have I done? Good. Хорошо, товарищи. I should probably not introduce too much. I'm going to introduce you to the Soviet system one little bit at a time, I think. All right, good. All right, so that makes sense, yes? That's the discounted value of the discounted marginal utility tomorrow has to be equal to what I give up today. Then I'm indifferent. Great. Okay, good. Yes? Yeah. And so then I can just go ahead and rewrite this, and I'll get the present value of this future unit of consumption, which is xt is equal to, and then I'll simply, that looks like e to the minus rho t u prime of ct all over u prime of c naught. Okay? Okay, yes, right? That was easy. Great. I want to take this and work with it a little bit more, and so let's get this out of here. We're going to end up with something kind of like this before we're done, I hope. Let's see what we end up with. That's the present value of a future unit of consumption, but what I want is the consumption discount rate, okay? That consumption discount rate is going to be, we'll call it RT. It's that thing. And it must be equal then, if I want to get this thing expressed as a rate, it's going to be, here. Move it down here. Makes up a little bit of space. RT is equal to D. XT dt over xt, and that's simply because the rate of change of a variable over time equals the time derivative divided by the variable. Okay, it's like a percentage change sort of thing, right? Okay. Good. And that, because xt equals that thing, can be rewritten this way, which is equal to d. This is a lot of algebra, but not really complex. E to the minus RT, especially if I write everything down correctly, u prime of CT, dt, all over e to the minus rho t, yep, oops. All right, good. Okay, and I can take the I can take this part out because that's just that's not a function of CT. It's not a function of T. That's just whatever it happens to be, right? Okay. With these, I should probably mention that with, I guess I didn't say this, but when we start out, a model like this, I started out with that thing that I was trying to maximize. We have to start out with given initial conditions so that we have a given initial capital stock of K naught, and then everything else will kind of evolve from that. And of course, we have the production function and everything else. So given the initial starting point, so we know what the starting capital was, and that should give us this thing. It isn't really something that's a function of time. Okay, good, wonderful. Now, what are we doing here? Then I'm just doing, taking that derivative, using the rules of derivatives, I get, this is lengthy but not too complicated, minus e to the minus RT U prime CT. Excuse me. Thank you. E to the minus rho T U double prime, second derivative, CT dC dt all over e to the minus rho t u prime of ct. And really, I should have put a negative on this because I want the absolute value of that thing. And we know that this thing is decreasing over time. And so I put the negative number there and negative number there, which means that since that was a negative row, now I can just quit worrying about those signs. Okay, great. So that's where the negative row turns into a positive row, so to speak. Okay, good so far? Yes? Now, because I have a board that it's easy for me to work on and you don't, I'm going to do something else. Like I'm going to take C over C and plug it into all this stuff, right? That's one, okay? Cool, so let's do it. I'm gonna rearrange it a little bit differently. I'm gonna put the C right there and then put the thing that I just erased, which is the DC C. Okay, so I've got C over C. Right, so all I've done is put a 1 in there, but that's a useful term to have, and then I can have that separated out because that just gave me the growth rate of consumption over time, the rate of change of consumption over time, and I think this is what I was looking for, because what do I have here? Well, let's see. If I do the division of that and that, I end up with rho. And I do the division of that and that, I end up with that in it. Oh, that's the, let's just rewrite it and look at it. That's actually equal to rho minus u double prime CT. I'm going to make sure I don't do something foolish, so I'm going to look at my notes carefully, but that seems like, yep, that's gone. So that, and then I've got the C right there, C, T. You can put the T's in there, just if I want them. And then, what else do I have? CT, and minus, or not minus, it's times. Yep, get that there, yep. Okay, good. Now what was I calling this one? The elasticity of the marginal utility of consumption. Well, that's exactly what that is. Yes?
I was just checking, so from like the E, everything parentheses, divided by dt, all you're doing, that next line is just writing it out, that derivative. Right?
Going from here to here, yeah.
Okay. And
Yes.
then wouldn't the CTs cancel out in that situation? Because it's CT times something over CT.
Like here. They did.
No, in the red, the CT times.
They do.
Okay.
Yeah. That's why I get to do that.
Oh,
That's why I put them in. I stuck them in. I did that in 2 steps. That's 2 steps right there, right? In my notes, that's 2 different lines.
okay.
And I'm saving markers and board space.
Okay.
And that's why I say I'm cheating. That's why I change colors. In your notes, it should be different. Those should be different lines, right? Okay. Because first of all, I had that. And then I said, well, I may as well just add C over C. But I'm going to separate them in certain ways because when I put that C with that, oh, that's got another name. That's the marginal utility of consumption, right? That's the elasticity, I should say. That's an elasticity formula. Okay, great. That's the elasticity of the marginal, I was calling that eta, that thing right there. And what's that? That's the gross rate of consumption. Oh, look, that's where that stuff comes from. So even though it was magic, and it's still magic, there's some logic behind the magic or something like that. Okay, that makes sense though. You can see how I suddenly jumped to all that. Okay, at least that was my idea, to show that. Okay. Good? Okay. This takes me back to my PhD program, because that was where we did a lot of this stuff, like in a macro class, something like that. So if you see me start becoming shaking and post-traumatic stress syndrome sets in, you'll understand. All right, good. Okay, awesome. Well, that was the logic behind all of this and why that would be how we get that discount rate from the Ramsey rule, in other words. Okay, good. It makes a sort of sense. Awesome. So let's talk then, it's just sort of a recap about these integrated assessment models, which are used for the climate modeling. And so first of all, it's a kind of modeling where first of all, it contains the following things. You have carbon dioxide emissions and the expected effects that would have on the carbon stock in the atmosphere. So this is what we have to estimate for the IAMS. For the integrated assessment models, first, we estimate CO2 emissions or carbon emissions. It's not just CO2, but and effects on the carbon stock in the atmosphere. Okay? So that's the step. Next step is the effects of the carbon stock on temperature. Okay, great. Or on climate change. Maybe there's some other effects we want to look at. But then, that's not enough. What are the effects of the climate on economic variables? Okay, great. And then there's a fourth thing we have to take into account, which is discounting. Great. And so the standard model would be one that it comes from, so for example, from Nordhaus. He has the DICE, which is the Dynamic Integrated Model of Climate and the Economy. And what it is, the latest version of that, it comes from Nordhaus. And his latest version is called DICE 216 or 2016R. That's the latest version. And what it is, it's a Ramsey neoclassical growth model, like what we went through here, kind of, and then adds in climate damage and climate investments. Climate investments being expenditures on abatement, on somehow taking care of emissions. Great, so we add those components to a standard economic model, and there we get it. Okay, cool. I guess. Yeah, it is. It actually is kind of an interesting procedure. So, great. How are we so far? Time. Okay. Let's. Let me ask if there are any questions, or take a breather for a second. Okay. I'm going to give you a sort of a version of this that will maybe get the point across of how the hoteling model works. Because to fully go through one of these is beyond what we are going to do in this class. We're going to have enough work going through the Lemoyne and Rudick version. So let's go ahead and I'm going to give a rough explanation of the hoteling rule that the standard model has called for in carbon pricing. That is, this one will give us a hoteling rule that says, if we're going to put on a carbon tax to control emissions and keep them down below some level, great, here's how we would do it. We could use this hoteling approach that comes out of this model. And so it's a Ramsey model with all these things put into it. And so here's what we're doing. We will choose abatement. That's the control of carbon emissions. And that's AT to maximize. So we're going to maximize is from 0 to forever. The discounted value, and we'll just use an R for it, of CAT dt. What is this? That is simply the cost of it. We're going to minimize the cost of abatement, okay? And the discounted value of all the abatement we do all over from now till the end of time, okay? We want to minimize the cost. The way you would do that is just not to spend anything, but there's a constraint. The constraint is that we don't want to put out too much carbon, and so we have to bear some costs for that. And so this is going to be, here's our constraint, m dot, that is the change of, that's going to stand for, we'll explain it all in a second, but m is going to be the amount of carbon that we have in the atmosphere, okay? That's the carbon stock, and that's the change of it over time, will be equal to E minus AT minus delta MT minus M pre. And I'll explain all this here. So what is that? That's simply the change in carbon stock at T. In the atmosphere at T, okay? That's how it's changing over time. This is going to give us the path, and that must be equal to our emissions, how much we're putting out, and that's going to be exogenous. That's just going to be what's coming out, something like that. There's the cost, or sorry, yeah, there's abatement, not the cost, but the amount, we're going to minimize the cost of that, but that's taking carbon out of the air, right? Right. Okay, good. And then we have delta. This whole thing will be, that's going to be the decay of carbon in the atmosphere. And this, as we'll see, is the excess carbon. And so that's the total, and that's the natural I'll just call it natural right now, but the natural carbon means pre-industrial or pre-man or something like that. And there's the total carbon, right? So this is the difference. This is the additional carbon that human beings are putting into the atmosphere, right? That's the total amount. Take out that's naturally there, and you get the total amount that human beings have put in. That's anthropogenic generated. That's the idea. How fast is it decaying? Okay, we have to subtract. Humans are adding to it, but to this, but we have to take out the decay because we think that the additional stuff must be decaying, and we also that we get rid of by abatement. Okay, so that makes sense. And then we also have another barrier, which is that MT, our stock, has to be lower than, less than or equal to M. What should I call it? I don't want to call it naught. Call it bar, I guess. I don't know. I'll call it maximum tolerable, okay? And then I'll put a bar over it. That's what that's gonna mean. That's the maximum we're willing to put out. Beyond that, oh, the global warming will be so bad that we just can't survive it. So if we think, for example, that 2 degrees global warming, 2 degrees average warming is the max we can tolerate, that would set a boundary on how much carbon we can put out, and that's what I just put down there, okay? Great, yes? And we also know that M naught is given. And so those are our constraints. So subject to that, and that, okay? Right. That's the law of motion. That's the boundary that we don't want to exceed, and that's our starting position. Wherever we suddenly dawns on us, we need to do something about this. Got it all set up, and that's what we're going to try and minimize. That all makes sense. I can logically explain that, and you can see what's going on. Okay, cool. If we just then start working through that, I want to solve a simpler problem that gets the point across. So again, what we're imagining is that the atmosphere is a reservoir. We can fill it with carbon. There is a benefit to doing that. You don't want to have to take all the carbon, all of the gases out of your tailpipe when you're driving, and all of it out of your industrial processes. And it's a lot cheaper and easier just to dump it in the air, right? Right. Yep. Okay, good. If you don't think so, tell me what you're going to do when you're driving. And don't be like my friend who rides his bike and says, see, I'm not contributing. Yeah, well, your bike is a custom-made bike, my friend. And it was made out of metal, and it was shipped from Colorado, and you're breathing. So stop. Anyway, it is a cool bike. It cost him $6,000, $8,000, I think, actually. Custom. What's that?
You can buy a couple used cars for that.
I once bought a pickup truck for $450. This is great, too. Anyway, that's of course, that was back in the old days when the dollar was worth more. It probably costs $1,000 now. So here's what I'm going to do is model, my simple model is going to be PT, that's the benefit, okay? And that's going to, oh, this will look so familiar to you, AB minus Q2. Okay? I'm just going to say the benefit is linear, okay? And QT is the carbon dumped in atmosphere. I'm calling it dumped, but put out atmosphere at T. Okay, and I've got it as this kind of a function where the first unit, it's going to be really expensive to get the first unit out, but at some point, I don't know, when you're putting a lot out, you just cut back or something. So at any rate, delta is my rate that carborn, I sound like I'm from Maine or Massachusetts. Carbon, that's my rate of carbon decay, and per period. And Q bar is like that. I'm using Q because we're used to carbon consistent with a warming target. Great. Somebody decides what's the maximum warming we can tolerate and sets that target, and that will tell us what the maximum amount of carbon we can put out is, right? Okay, good. All right. And so the dumping, though, is not priced. You can put this stuff out. Nobody charges you when you're driving around in your car or when you're running your factory. You're not paying for the exhaust you're putting out. And so the government is going to have to intervene and set a carbon tax that will price that carbon that everybody will have to pay. Well, what's the proper price? We want to figure out what the value is, and then we can price this thing. And so I think my model that I concocted this one because it's an analogy. I'm not 100% certain that I've got this right, but I think it certainly shows the logic of what's going on here. But I'm going to choose QT to maximize, and I'm going to have the sum of, from time t today to infinity, go forever, and it's going to be 1. The discount factor that I will use is 1 over 1 plus r plus delta. I'm going to put that carbon decay in there. And then I simply have my usual I want the total benefit, QT minus 1/2 BQT squared. Okay, great. Subject to my constraint of the sum of the QT has to be less than or equal. I will not allow myself to put out more than that. I can't have more than that, right? Right. It's a benefit to dumping this stuff out, but I can only put out so much or I will exceed my gains or whatever, okay? So I already know if I set that up as a Lagrangian, all of you know we all know that LQT for all t, for all qt, we know that our first order condition will be that 1 plus r plus delta to the minus t, okay, but shoot, come back. Here's the t, gotta get the exponent on there. Okay, so just inverted it. A minus b qt minus lambda equals 0. We set that equal to 0. And that again holds for for every single period, that holds. That is to say, that is equal to lambda in every period. But of course, that is the factor that keeps changing. And so I can rewrite the first order conditions and get my Hotelling solution. This is the Hotelling solution. My Hotelling optimal path would be sum of the q star t from t equals 0 to infinity. So a whole bunch of those, how much I'm going to do in each period, solves that for all the periods, or in other words, it's the solution to that for all those periods. And one thing I find from this is I would get 1 plus r plus delta, and of course, what's another name for this? PT, in other words, the marginal benefit, right? I mean, PT equals that, so I just plug in a PT. I'm saving ink. Okay, great. Right? Right. Okay, good. So in other words, the price of carbon is going to grow at the rate of interest plus the rate of decay. That's what that's telling us. And So my earlier carbon emissions will be discounted less, and they're going to have more time to decay. Hence, we get the hoteling solution, the optimal path. Can that make sense? Great. We've chosen our path for how we're going to put carbon out into the atmosphere, and then we'll set the tax accordingly to get that to happen. Yes?
Sorry, you said early something would be produced less than so.
Yeah. Which one's bigger, PT or PT plus 1? Okay.
Or PT plus one.
PT plus 1 is bigger. That's a positive number, right? So PT plus 1 is bigger. We see that. PT is less than PT plus 1. Which one's bigger, QT or PT? Sorry, which one's bigger, QT or QT plus 1? If that one's less than that and they have an inverse relationship, it must be that, right? Right, okay. Because it's, I did it, it's downward sloping. Great, awesome. Okay, so what that's telling us is that we're putting out more carbon now, letting it decay, and then we will put out next time. Okay, and taxes must be increasing over time as well, right? Okay, the carbon tax. Okay, we're trying to get ourselves on this optimal path, and that's the hoteling path. That's basically what it is. So that at least kind of illustrated it, even though I think I don't want to present this model at the AEA meetings or something. Not that they would let me, but at any rate, so that gives you the basic idea. Cool, huh? Guess what? It's wrong. According to Lemoyne and Rudick, it's wrong because here's what it has done wrong. Before I say this, is it clear what I'm getting at? Or is it clear what I've written here? Any questions about it? Gabe, make sense? Or Adam, Connor? Straightforward. I woke up this morning just imagining this myself anyway. It's always yes. All right, good. Everybody's on that side of the room. I guess this side of the room is always happy, so. Which makes me think they're really delirious. All right, good. Oh, good. Where are we? It's wrong. Why is it wrong? Well, here's what Lemoyne and Rudick argue. It did the wrong thing. It focused on carbon stock and not temperature. We don't care about the carbon. Suppose that you put all the carbon in the world, but it doesn't have any effect. I don't really care about carbon. I care about the temperature. Okay, so that actually makes a difference. In fact, that's the only thing we care about is what is the effect on climate. So maybe we should be focusing on a climate effect. Well, of course, it comes through carbon, but it's not instantaneous. In particular, temperature effect, there's a lag between when you put it out and when it has effect, and that's apparently pretty well understood in science. I don't think it's exact, but they understand that there's this lag. And so the least cost path has to take that into account. That is, it has to focus on, so this focuses on carbon. But it should focus on temperature. And unless carbon is instantly converted into temperature change, this is wrong. Because this works over time, and it's not instantaneous. It actually makes a difference. So they go ahead and rerun a model that focuses on temperature, taking this lag into account, and they get wildly different results. It's not that, oh, there's a little bit of a tweak. It's wildly different. And that might make a huge difference. The hoteling path that has been calculated might be all wrong because we've done the wrong thing. That's their argument. And not only that, there are other factors that get involved in this. And so their paper from 2017 tackles this. The one guy, Rudick, he's listed at Iowa State University. He got a promotion basically because of this and a few other things. Because when this came out, I contacted Chris Pudens. I said, do you know Rudick? And he said, oh yeah, we just lost him. He went to Cornell, where he makes a lot more. It's a higher prestige university. These guys, anyway, they're pretty famous. Or infamous, I don't know. But at any rate, so we're going to go through that paper next time. Because I've got, 7 minutes? And I think I can't do it that fast. But they're going to study things like what they call inertia, forcing. So forcing is the rate at which temperature changes given carbon changing. And that's just the term for it. It's the rate at which it happens. And so inertia is going to be inertia. How long do you have before things take effect will be crucial for calculating the least cost carbon dioxide policy. And what they find is that the optimal policy is much less radical in the near future, but more radical in the far future, as far as taxes go, or lower tax. So it's something, again, what I had drawn before, we end up with carbon C2 emissions here in the stock, or the C2, it's really the C2 stock that I want, carbon. The carbon stock in the atmosphere and time. And so if this is hoteling, something like that, and we're approaching our barrier, what I'm calling there Q bar, I guess. We're approaching there. They have something that's different, and theirs is something more like, I don't know, what do you want to say? I think there's even, if I goes a little, can go a bit above there and overshoot. But a lot of people don't like the idea of overshoot. They think it's dangerous, so we would overshoot. IPCC, UN. And so you get something like this where it's higher, but then it's becomes more, obviously at some point it becomes more draconian. I think I drew that not really sensibly. Theirs is like this, something like that, okay? So at some point you're picking up that extra growth in the near future and then making up for it with higher taxes later when you're rich, so to speak, okay? Great, make sense? We're gonna work through the model next time and see how far. So now I think maybe you can pick up this paper and at least get some idea. You can read it. You'll be able to read it. Sit down and work through it. Write yourself a set of notes, step by step, what's going on in the model. You can understand this. It isn't like this is going to be impossible. They don't even have to get, a complete solution to this thing. They do it in some appendix, but all they really need to do is they don't actually even calculate a path. They will later calibrate it. They just get the basic principles down, and they get how the thing works, and then what that would imply. So at any rate, good. I'm going to work through it carefully next time. Oh, the other thing I wanted to say is, if there are no, I'll ask questions in a second. We'll finish this paper next time, I'm pretty sure, and then we'll move back into Dixit, because I know you've all been anticipating it with great excitement. I see Gabe suddenly broke into great delight. Was that a drop card you have there? I can't tell. But I think what I'll do is we're going to skip this chapter on uncertainty for now. We'll come back to it. But since we're doing dynamics, let's just move into chapter 10 and then chapter 11. Those will be a couple of lectures, and I'll be, again, kind of arm waving. But we'll get you through the idea of dealing with optimal control theory and dynamic programming. So go ahead and be ready to start working on those chapters as well. Okay? And then we will do them kind of. All right. And then we'll return to uncertainty. We've always had uncertainty in the background, right? All right, good. Any questions?